Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Dafda, and in this 70-second video class of DIP, we will study patterns and pattern classes in object recognition for digital image processing and its implementation in MATLAB. In our previous few video classes, we learned representation and description, and now we will learn the final step of digital image processing, which is object recognition, or we can say object identification. Okay, starting with the name. What is the meaning of pattern? Pattern is basically an arrangement. For example, ABC, ABC, ABC is a pattern. Okay. And what is the meaning of pattern class? Pattern class is a family of pattern. If one pattern is ABC, 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 and the second pattern is XYZ, 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 then both belong to the same pattern class. Okay. So let us start. These are the main steps of image processing, and now we are learning final step of image pattern classification, interpretation, or object recognition. That basically completes our image processing task. In our first video lecture of DIP, we understood that there are three levels of image processing: low level, mid level, and high level image processing. And object recognition comes under high level image processing. And see, object recognition is a difficult task that performs functions associated with visions. Okay, and for computers, it is very difficult to recognize objects themselves. Let us first see the introduction to object recognition. See, the automatic recognition of objects or patterns is one of the very important image analysis tasks. An object recognition system is like a computer program that tries to identify the pictures of the real world. It does this by using models of objects that it already knows about. So this is a tough job because it's not easy to teach computers to do this. Humans, on the other hand, can recognize the objects in the picture without any effort and also really quickly. The object recognition methods can be broadly classified into two categories: decision theoretic methods and structural methods. As the name suggests, the decision theoretic methods takes the decision theoretically from the values which it gets. So these methods deals with patterns described using quantitative descriptors, okay, and have patterns arranged in numeric vectors such as length, area, texture. So what is a length? That is a quantity. What is area? What is a texture? Those are different quantities, and therefore this is known as quantitative descriptors. Whereas the structural descriptors or structural methods of object recognition deals with patterns best described by qualitative descriptor or symbolic information. So it doesn't exactly deal with the values, but rather some symbolic information such as relational descriptors for repetitive structures. For example, the staircase, right? So here the patterns are arranged in strings or trees. So some strings may be repeating, or some tree structure provides the qualitative information. Any of these both methods can be used, but the central idea is learning from sample patterns, which is also known as machine learning. So the next step of image processing is the machine learning and artificial intelligence, where the computer or the machine learns itself that these are the objects or these are the things that needs to be recognized or analyzed. So object recognition means pattern recognition, right? And these pattern arrangements can be in three different types. One is numeric vectors, which is a quantitative descriptor, and other two are strings or trees, which are qualitative descriptors. So you'll be learning in detail the numeric vectors and the strings or tree pattern arrangements. Okay, let's go ahead. So in patterns and pattern classes, a pattern is an arrangement of descriptors or features, and we have studied representation and description in the previous chapter. So those descriptors for pattern recognition can be quantitative or qualitative. A pattern class is a family of patterns that share some common properties, and the pattern classes are denoted by W1, W2 up to Wn, where n is the number of classes. Pattern recognition by machine involves techniques for assigning patterns to their respective classes automatically and with as little human intervention as possible, and that is only artificial intelligence. Okay, so the object or pattern recognition task consists of two steps: feature selection or extraction and feature matching or classification, which we will be learning in detail in this chapter. And as we have just discussed, there are three common pattern arrangements which are used in practice. One is numeric pattern vectors for quantitative descriptors, where the pattern vector can be x is equal to x1, x2 up to xn. Number two is strings, and number three is trees, which are for qualitative or structural descriptors. For example, x is equal to AB, 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 a repeating string, right? So as we saw here, the pattern arrangements that you will be studying will be numeric vectors for quantitative approach and strings or trees for qualitative approach. Okay, let us first understand numeric pattern vectors. Sir Fisher in 1936 performed recognition of three types of iris flowers, that is iris serosa, iris versicolor and iris virginica, data by the lengths x1 and widths x2 of their petals. So this is x1, that is the petal length, and this is x2, that is petal width. In this graph, iris setosa is shown with circles. So these are iris setosa. Iris versicolor is shown with squares, and iris virginica is shown with triangles. So here three pattern classes are W1, W2 and W3 corresponding to setosa, versicolor and virginica, and because the petals of flowers vary in width and length, the pattern vectors describing these flowers will also vary not only between different classes but also within a class. Here each flower becomes a point in the 2D Euclidean space. For example, for this particular versicolor flower, the petal length is 3 point something and the petal width is 1 point something. One other point to note over here is that the measurement of petal width and length adequately separated the class of iris setosa from the other two, but did not separate versicolor and virginica types successfully from each other because here they are overlapping. So this result illustrates the classic feature selection problem in which degree of class separability depends strongly on the choice of descriptors selected for a particular application. Let us understand one other example for numeric pattern vectors. This figure shows a noisy object and its corresponding signature, and these signatures we have already learned in our video lecture number 67, and here we represent each object by its signature and form the pattern vectors by letting x1 is equal to r theta 1, x2 r theta 2 and so on. But now instead of using raw sampled signatures, a more common approach is to compute some function xi is equal to g of r theta I of the signature sample and use them to form vectors. That means we are modifying the signature with some function g, and these vectors becomes points in n-dimensional Euclidean space, and pattern classes can be imagined to be clouds in the n dimensions. So for the moment, the key concept to keep in mind is that selecting the descriptor on which to base each component of a pattern vector has a profound impact on the eventual performance of object recognition based on pattern vector approach. And see, instead of using signatures, we can also use other shape characteristics such as statistical moments, and this may give better results, right? So the choice of descriptors has a profound role in the recognition performance. The second type of pattern arrangement is the string descriptors. So rather than the methods which we just saw in the previous few slides, in some applications the patterns are best described by structural relationships. For example, the fingerprint recognition. It is based on interrelationships of print features which are called minutiae. So together with the relative sizes and locations of the print features, the other primitive components that describe fingerprint rich properties are abrupt endings, branching, merging, disconnected segments, etc. So recognition problem of this type, in which not only quantitative measures about each feature but also the spatial relationships between the features, are best solved by structural approaches. And this fingerprint example we have already studied earlier also. One other structural method example is the staircase pattern, which is described by head to tail structural relationship. So this is the head to the tail structural relationship, and here the rule only allows alternating patterns of A and B, and it excludes other types of structures, but of course other rules may be defined. And these string descriptors adequately generate patterns of objects and other entities whose structure is based on relatively simple connectivity of primitives, usually associated with boundary shape. But a more powerful approach for many applications is the use of tree structures. So that is the third type of pattern arrangement. Basically, most hierarchical ordering schemes lead to the tree structures. In this example of satellite image, the structural relationship is defined as composed of downtown area and surrounding residential area. So the image has the tree branches like downtown area and residential area. The downtown area has further branches like buildings and highways, and residential areas have further branches like housing, shopping malls, highways and so on. And see here, the root of the tree describes the entire image. So we can go on subdividing until the resolving capability is reached. So in this way we can use different pattern arrangements in patterns and pattern classes. Now let us implement in MATLAB how a square pattern is detected out of square, circle and triangular patterns. So that is all for this video class. I hope you would have gained a good knowledge from this video lecture. Thank you very much.